So I'm here to talk to you about a concept I've been working on called Optimus Energy, with the overall headline of digitalizing the battery value chain to enable the energy transition. And I don't think I need to convince anyone here that the energy transition is something that we must go through. And I think it's also not a far jump to say that batteries are essential to achieve the energy transition. But if we take that one step further, batteries are needed across the spectrum for enabling the electrification of transportation, deploying renewables on the grid, and countering the inherent intermittency in renewables, and various other applications across the spectrum from mobile devices to long-distance transportation. Putting that into numbers, I was actually just looking at a new report that was putting the growth at 34% per annum. Regardless of who you believe, the battery industry is growing incredibly quickly. We're looking at somewhere between 6 and 10x between today and 2030. But that's coming with a lot of challenges. And so before I jumped into this project, I had already conducted a bunch of interviews with various people in the industry and came to the conclusion that the top 3 things that are going to hold back the battery industry are the availability of raw materials, where inherently we just need to mine a lot more materials for batteries. Secondly, we need new chemistries, specifically for niche applications, including long-duration storage on the grid, as well as for long-distance transportation. And lastly, manufacturing. We need to make a ton more batteries and to become much better at it. So with that, briefly on me. My name is Thilo. I hold a background in aerospace engineering, and I got into batteries through the company I worked at before Stanford. It's a company developing battery electric aircraft. And this was in the early days of the battery industry, where we were blowing up battery cells behind our hangar to make sure that our aircraft wouldn't blow up midair. And just to put into context of the challenges with the battery industry, my role was building factories, and the first factory I built burnt down because of a battery fire. I came to Stanford. I'm currently in the last touches of the MBA and MS, and I'm also working part-time for a company developing a novel battery chemistry for aviation. Now, with all that, the challenges in mind and my background, I framed my Capstone project around this quote. I heard this quote independently from several people I interviewed. Batteries are stuck in the dark ages. And so the research question I went out with is, what role can technology play in accelerating the battery industry? To do this, I mapped out the battery value chain, starting from research and development of new chemistries through the manufacturing process, integrating them into products, their deployment, including financing and insurance, operation, all the way down to the second life and recycling of batteries. I set out into the project wanting to conduct at least 30 interviews to outline a business plan for what a company could look like that would serve somewhere in this battery value chain. And I'm currently in the finishing touches of putting together a LinkedIn blog post to also share some of these findings with the wider world. And so what I've actually done is conducted more than 40 interviews, counting everything in. It's actually approaching 80 at the moment. I visited 2 facilities and tested 3 different business models throughout the Capstone project. So let's look into what that actually resulted in. I discovered a number of different things, and this chart is a little bit of a mess, but I think it's quite helpful to have it all on one slide of just what are all the things that need to happen for batteries. And these are the biggest highlights up here in this corner are the takeaways where I see high feasibility of addressing them with new technology, and they have a high importance to the industry. They come from developing new chemistries for long-duration storage, solving the lack of battery modeling engineers, where there's a real shortage in the industry, all the way to improving the manufacturing process. I took these things and mapped them back onto the value chain I just showed you. And across each of the value chain steps, there are key things that technology can enable and will have real value. And so to test this out, I tried a few business models. The first one was looking at the material discovery and cell design phase. In this process today, a lot still runs on paper. Some companies have built in-house tools, but truly, good deployment of technology could accelerate the R&D process, meaning we get better chemistries faster and decrease the cost, resulting in cheaper cells overall. What gave me a true tailwind here is that there's lots of custom-built solutions. Almost every battery company I talk to has built something in-house to try and manage their data, their workflows, and so on. But none of them are particularly happy with what they have. In fact, when someone says, is it a hair on fire problem? When I talk to Tesla, who you would think is the most advanced in a lot of these topics, they're running around scrambling between different sources of paper, Excel, and God knows what else, and are really desperate for something better. But from a market size perspective, thinking about this as a business plan, I also came to the conclusion that this is inherently a very small market. And so I expanded the aperture a little bit. What happens if we look at the whole value chain? And there's good analogies from this, for this from other industries. If you look at the semiconductor industry, the software stack from EDA solutions, electronic design automation, that have really penetrated across the value chain now, have created multiple tens of billions of dollars per year of value for the industry. And so I asked myself, could something similar be created for the battery industry? And the conclusion was that there would be incredibly high value for this to be done, particularly as you can start integrating data, where batteries are a system that is poorly understood today. Once you have data from deployment from the operation and feed that back into the R&D phase as well as the manufacturing phase, there is a lot of improvements across all of these steps that can be had from putting it all together. But again, despite being a fast-growing market, the battery market is fairly small as it is, and the willingness to pay is not high. So I focused in on one more, manufacturing. And the reason for focusing in on here was that the thesis that if something gets built for battery manufacturing, this could be expanded to many other industries that need manufacturing at scale, particularly with the tailwinds of reshoring and many new technologies coming to market. Other things in clean tech that are very similar include electrolyzers as an example. So let's dive into this a little bit more. At a high level, domestic manufacturing is making a comeback. And there are billions of dollars going into this. In the US, we're looking at $300 to $400 billion as part of the IRA being invested into domestic manufacturing. In Europe, a similar amount was just unlocked with the European Net Zero Industry Act. And so there's a huge tailwind, but manufacturing is struggling with high scrap rates. In the battery industry, that's roughly 10% on average, but new battery factories are closer to 50% of battery cells at the end of the process that are just not up to quality, and many other inefficiencies. And so I came up with a thesis to build a solution that could reduce scrap, manage risk, and increase efficiency across the process. I'm going to jump ahead a little bit just in the interest of time. But I was blown away throughout the process just how consistent these pain points are. No matter who I talk to in the industry, they would have the same pain point come up over and over, yield, 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 and have incredible urgency behind it. And so I worked together with some researchers at Stanford who have been investigating this, looking at hybrid modeling, taking the battery manufacturing process and modeling it with a physics-based model, and then combining that with machine learning. Initial models for this have been developed, and I'm confident that this can work in practice. From a market sizing perspective, again, the market is not huge by itself, but it's sizable enough to get started. And once you start targeting other advanced manufacturing industries, this becomes really interesting. Just to sum up briefly, I started with the challenge of batteries are stuck in the dark ages, and found that many valuable solutions need to be built to accelerate this industry. But market size continues to be a constraint with the battery industry by itself. And so I focused in on a horizontal manufacturing solution And I'm going to continue this research beyond this capstone, and I'm actually going to be visiting a bunch of factories next week. And the key question that I continue to be centering in on is, how can we turn a good product, something that could create a lot of value for this industry, into a good business as well? Thank you.
Better questions than me. Just one of your slides when you talked about the sort of government mobilization of funding, both in the EU and in the United States. Are there any other sort of policies or steps that can be taken in the public sphere that you think are useful for addressing any of these questions? And it's totally fine if the answer is absolutely not. But just asking out of curiosity as someone who works in that
Yeah.
space.
There definitely are, and there's some interesting things coming up now. So one example is the EU passed a act called the Battery Passport, where every battery needs to have labels with it that include what recycled content is in them, as well as how to recycle the battery cell. And it's sort of an initial step to ensure circularity. A similar law has been proposed in California, and I don't know the latest of it. But I think if both California and the EU have implemented this, that'll create critical mass to have this deployed at least everywhere in the West, given that manufacturers are not going to do different things between these states and the rest of their products. So I think there's some exciting things coming up there. I do think that more needs to happen, particularly when you're thinking about this problem of having different actors in the different steps of the value chain, where you could unlock a lot of value, both in terms of money, but also just in terms of like how fast we can deploy new solutions, how good they are, by starting to share more data between them, by having collaborations and sharing know-how between these different value chain steps. And there's still a lot missing there. Some things are happening with vertical integration from automotive companies. I think policy can also help to accelerate some of those things.
Congrats, Theo. That was a great presentation. My question is regarding the composition of batteries. Are we like facing or are companies who have like a tunnel vision, or using like I'm going to use lithium or sodium, or are they very nimble in changing one another and trying new things out? What's your perception of that dynamism they can have?
Yeah, I think the industry overall is very conservative, and if you remember the chart I had just on battery demand, 90+% is the automotive industry or mobility, and they're increasingly centering in on 2 or 3 lithium-ion chemistries. Everyone wants to have the option value to, like, when new chemistries get mature enough to be able to start using them, but I think inherently they just want to get this stuff working first, and so everyone's focusing in on mostly increasingly LFP, but generally different types of lithium-ion chemistries.
Yeah. So earlier you mentioned the semiconductor industry, and one thing that I've noticed, or the comparison to the semiconductor industry, I've noticed that recently a lot of tech companies, instead of relying on outside manufacturers, semiconductors like Intel and Qualcomm, they're trying to bring it in-house, like Apple's doing their own chips. Do you see something similar happening within the battery space in the future, with it becoming more fractured, where people bring battery manufacturing in-house, or do you see it playing out differently in the battery industry?
I think it's actually really interesting that the battery industry is taking a lot of the analogies, and I think when you look at the semiconductors space, a lot of these companies are developing their own chips, but they're not manufacturing them themselves, but rather relying on contract manufacturers. And the battery industry, right now, there's sort of 2 things that are growing. On the one hand, you have the automotive companies building their own plants, and then you have a ton of new contract manufacturers that are starting to grow. Freyr is one example. They're building a plant with Koch Industries in the US, another one in Norway, and a few others. And they're really relying on other people developing the IP, and they only do the manufacturing. And that then is very similar to, for example, the TSMC model, where they develop the manufacturing know-how, but they leave the design to someone else. And so here it'd be someone designs whatever chemistries they want to have. Then you have the actual materials provider. So it's like an anode material provider, cathode material provider. And then you have the manufacturer as a contract manufacturer. So TBD if it plays out like that, but that analogy is starting to form.
Can you show me the slide you skipped really quick? Awesome.
This one.
Brilliant. Talk about that slide for the last 20 seconds.
Yeah, this was just a brief slide on the technical side of what is hybrid modeling. Since I briefly touched on it, this combination of physics-based and machine learning modeling. And this is sort of a nascent field in machine learning that's only really developed over the last few years. Pharmaceuticals is the space where it's been used the most. But the interesting thing with it is that you use physics-based equations to constrain the problem from first principles. And then, in effect, need only about 1% of the data. It's much easier to train models. And you're much more robust in the results in predicting things in the future that are outside the training scope.